So if the receiver size is very small, suppose this receiver size is very small, and there's a laser beam, and in the atmosphere, because of the turbulence, there may be this laser beam will be either deflected, scattered, then you might miss the receiver. So there will be a lot of fluctuations which will happen in the receipt power. So if you see receipt power versus time, the power will fluctuate because of the turbulence. So let us now understand what are the different techniques which can be used for turbulence mitigation. So one of the scheme is aperture averaging. Now in aperture averaging, as I explained in earlier, that there are eddies in the atmosphere. So there may be big eddies or smaller eddies. And suppose you have a point receiver here, then, and say this is the cone, and the light is collected by this receiver. This is a case of bigger eddies. For smaller eddies, you can have something like this. So this is your, say, point receiver, where the receiver aperture is not very large, and there are many smaller eddies inside the cone. So what happens that if this distance is, say, r, that is a range, and if I calculate what is the typical angle of the cone, say theta is approximately lambda by L, where L is the size of the eddy. So this is, for example, L. So that's a typical theta, and the theta max will be actually governed by the smallest eddy. So this will be lambda divided by L naught, where L naught is the dimension of the smallest eddy. And if I calculate the width of the cone, and designate this as D, so this width of the cone D will be R, that is a range, theta max is equal to D. So that is a typical width of the cone. Now, if D is less than L naught, that is width of the cone is less than the size of the eddy, in that case, the laws of geometrical optics will operate. Laws of geometric optics are valid. So let us find out a condition where we can have laws of geometrical optics. So D less than L naught, so this R theta max is D less than L naught, and the theta max is lambda by L naught, so this becomes R lambda by L naught into L naught, and this gives me an equation which is L naught greater than lambda R, square root of this. So as long as this condition is valid, the laws of geometric optics are valid. The other condition could be if L0 is less than lambda R. That means there are many smaller eddies or smaller cells inside the cone, and because of this, the light will get reflected or diffracted, and you are likely to get speckle pattern at the output because of smaller eddies inside this cone, which are as per this condition. So in the receiver, basically if it is a point receiver, then probably you will get only one speckle pattern, and sometimes there may be full intensity there, or there may be no intensity, so there will be a lot of fluctuation there. So if you use a bigger receiver, not a point receiver, increase the area of the receiver, then you may get several speckle patterns. So some will be high intensity, some will be low intensity, and you can add them and average out. So by increasing the area of the aperture, you can capture the laser beam or the light. So idea is to increase the receiver size rather than using a point receiver in order to get significant amount of receipt power. So this is called as aperture averaging, and this aperture averaging is we can define this by a factor, let us call it AF, where AF is the aperture averaging factor, aperture averaging factor. And this can be defined as the scintillation index when you have a wide receiver having received diameter as dr. So I'm denoting this as dr divided by scintillation index when you have a point receiver. That is, let me denote this as 0. So this is the receive aperture diameter. So this is how aperture averaging factor is defined, and we can calculate the ratio of this scintillation index when you have Rx aperture diameter of dr and scintillation index when it is a point receiver. So it can be shown that this is equivalent to 1 plus A naught, where A naught is some constant, into dr whole square into wavelength, then S0, I'll explain what is S0, and sec of theta. This is raised to power 7/6 and whole thing is -1, where theta is the zenith angle and S0 is a height calculated. This is atmospheric turbulence aperture averaging scale height. And theta is the zenith angle. It takes into account the slant, because when the wave propagates, it makes an angle, so it takes care of that angle. So that is why this sec theta is coming here. So this is AF, and we want this AF to be as low as possible. And for making this AF, let us see what are the parameters we can tune in order to get a low value F. So let me draw a curve, typical curve, which is for different values of dr and zenith angle. So this is, say, on the x-axis you have the zenith angle, the theta. This is zenith angle, and this is aperture averaging factor AF, and it is plotted for different values of dr, so it will be something like this. So this, for example, is dr is equal to 15 centimeter, this dr is equal to 20 centimeter, and this is equal to, this is 20 centimeter, and this dr is equal to 30 centimeters. So we notice here two things, as angle, and this is low value of AF, say close to 0, and this is high value of AF, high value of AF. So as the angle, zenith angle increases, the AF value increases, which gives a low aperture averaging factor. And as you increase the value of dr, then there's an improvement in the AF value. So in effect, the AF value, because we want this AF to be very, very low, which means, this quantity should, should be high, right? So point receiver should be able to capture all the light. So as AF decreases, to get AF decrease, there are, two possibilities. One is the DR should be increased, that is the receive aperture diameter should be increased, or the theta, the zenith angle should be, which is the slant angle which the beam makes with the normal, that should be decreased. So these are the two possibilities. By increasing the receiver aperture and decreasing the zenith angle, will make the AF value as low as possible. So this is in brief how turbulence mitigation can be done using aperture averaging. The other technique which can be used is spatial diversity. So in aperture averaging, in order to have, multiple speckle patterns on the receiver, the area of the receiver should be high so that I can capture, good amount of light. But the flip side is that if the area is high, then the atmospheric noise which is captured by the receiver is also high. So when you cannot increase the area of the, receiver aperture very high, because it will, also increase the atmospheric noise. So this is one issue with the average aperture. So instead of having a single aperture, let us think of having many such apertures, receiver apertures. So, and these receiver apertures should be kept very close to each other, and the distance between the two should be more than the coherence length, because what we want, that the received signal which is coming on to these receiver apertures, there should not be any correlation between them. So, and that is only possible if you keep those two apertures, or whatever number you have, it should exceed the coherence length, should be greater than the coherence length. So one of the simplest example could be, if I have, this is, say, for example, a driver circuitry for a laser. And this is the laser part, which is getting modulated. And then this is the laser beam. And then you have the atmosphere here. This is, say, atmosphere. And then you have 3 different receivers, for example, or there can be many. So this is a case of received diversity. There are 3 receivers, let us say, and this is RX1, RX3, and you get signal onto all these receivers. And the distance between these 2 receivers should be more than the coherence length, so that the signal received by these receivers are uncorrelated. So you get different outputs from here, which can be processed. So this is an example of a received diversity. So even if the light is affected by atmosphere, you will get signal in one of the receivers, and you can use different techniques for getting the signal back. So this is a case of receiver diversity. Similarly, we can have a case of transmit diversity. So in this case, you have the driver, for example, for the source, and there are many transmitters. So laser 1, laser 2, laser N. So I'm drawing here 3. So this is laser. This is laser. And all these laser beams, they are passing through an atmosphere. And then you have all the signal coming. They are collected by a receiver here. This is the receiver part. And then some sort of signal processing here to get your original signal back. So this is the data out. So this is a case of transmit diversity, atmosphere. And the third option can be, we can have a multiple input and multiple output, which means there are many transmitters and there are many receivers. So it will be something like this. So this is your driver circuitry, laser driver, and then you have multiple transmitters. Here I am showing 3. This is multiple transmitters. So this is laser 1, laser 2, laser 3. And then you have the atmosphere here. This is the atmosphere. And you have multiple receivers. So it is a case of MIMO, where you have multiple input, multiple transmitters and multiple receivers. So this is a case of MIMO. So using these techniques, either receive diversity or transmit diversity or MIMO configurations, you can mitigate the atmospheric turbulence. Let us now understand how this MIMO will help in reducing the improving the performance of the system. So let us try to understand this. Maybe we can remove this part here. So let us see what is the maximum input or maximum input you get at the receiver. So that will be a summed output. Let us denote that as IR will be equal to eta. This is some efficiency parameter which is converting from optical to electrical. So this is efficiency, because you will be using some device which will convert from optical to electrical. So this eta is the efficiency parameter, and then you will add the signals coming from all the receivers. So this will be summation I is equal to 1 to, or j is equal to 1. Suppose there are n receivers, then this will be j is equal to n, and then I signal, this is at the jth receiver, the current at the jth receiver, plus there will be a noise element, so I n at the jth receiver. So assume that all receivers are identical and they are getting outputs. So I'm trying to calculate the best case. So this will be eta, and then it will be n times I S1. That is the signal from the one receiver, and they are all same, so multiplied by n. And I can take this eta is equal to 1, so this becomes actually n into ISN. So this is the summed output. And if I calculate the variance, which is sigma square of the current IR, it will be n times I square S1 plus IS2 square, so on and so forth, plus I N1 whole square. So this will give me n, basically S1 square plus square n1. So this term will not be there. I'm sorry about this. So this term will not be there. So this is actually n times the same logic, assuming they are all identical. This will give me n I square S1 plus the noise part, and this is equivalent to n variance in the signal and variance in the noise of 1 multiplied by n times. And this is my noise power and this is my signal power. And if I calculate the signal to noise ratio, effectively for n such receivers will be SNR n, and if I divide, what I get is root n, because this will be root of this, so root n into SNR of one link. So basically there is an increase of root n times as compared to the SNR of one link. So effectively there is a improvement if I use multiple receivers. And similarly on the same ground I can calculate the noise power, and it will be noise power of n will be 1 by n of, it gets reduced by a factor of n as compared to a noise power in a particular receiver. So this will be S1. Sorry, this is N1. So there is a reduction of effective noise power. So using spatial diversity, you gain in terms of signal to noise ratio, and your effective noise power gets reduced. But such a receiver, where you have multiple transmitters and multiple receivers, it is actually complex and it requires more space, and also because of the space constraint, you can't have a diversity, more than one. So typically, more than 10 you can't have, receivers or transmitters at either side, and it will increase the cost. There may be issues regarding the timing accuracy. So these are some of the issues. Timing accuracy. So these are the few issues which are there when you use, MIMO structure for combating turbulence effects using spatial diversity. So this is one method, and the third method is use of adaptive optics, which is also called as AO. So in adaptive optics, what happens actually, there is an undistorted wavefront at the transmitter. So let me first make the diagram. So this is, for example, TX, and you have this is some sort of lens, and you have undistorted wavefront which is going to the atmosphere. So this is the atmosphere part. And these are undistorted wavefronts and distorted wavefronts. So when they pass through the atmosphere, these wavefronts, they are distorted. So these are the wavefronts which are distorted. So let me make this diagram, the receiver part here. After the atmosphere, so what I receive is the undistorted wavefront. This is, distorted wavefront, distorted wavefronts. And I use some sort of correction here, and it's a it is possible, in the atmosphere there may be some phase fluctuation. So in order to handle those phase distortion or phase fluctuation, these are the systems used in telescopes. So we are also trying to use similar system for FSO system. So this is an undistorted wavefront, and then you have some sort of arrangement which is, it's a control closed loop solution. So this is tip tilt correction. This does tilting of the tip. So and then also you have some mirrors which are deformable. So you can change the orientation of these mirrors, deformable mirrors, and these are actually controlled by a device which is called as wavefront reconstruction and mirror control. Wavefront reconstruction and mirror control. And these things, when they are reflected through this beam splitter, you start getting the corrected wave from here. And this also, there's a waveform sensor here, and this unit goes here, and this, the waveform, the distorted waveforms actually comes through a beam splitter, comes to the waveform sensor, and then this block is waveform construction and mirror control. It changes the mirror, which are deformable mirrors, and you get the corrected output, and which can be collected using some arrangement here, and this can be collected by a lens, and then this is a receiver. So basically, depending upon the effect which atmosphere produces, one can send some test bits or test patterns, and calibrate the system so that whenever the actual data comes, it is corrected by a set of tip tilt correctors and deformable mirrors. So basically the phase correction can be done, or whatever the fluctuations are there in the phase, they are corrected and it is received by the receiver. So this is how adaptive optics can be used for turbulence mitigation, which is happening in the wavefront. Another option is coding. Coding, as you know, is actually you add some bits, addition of extra bits. And these addition of extra bits can be used for error detection and error correction. So error correction and error detection. One option is to increase the transmit power, which may not be possible every time. So you use, insert some extra bits, and so that whatever errors have happened in the channel because of the channel turbulence, they are detected and they are corrected. So basically, you don't increase the transmit power, but use some extra bits. So the extra power can be traded against by adding, extra bits for error correction and error detection. So sometimes there are, in FSO systems, there are some burst effects. So you use interleaving techniques to take care of burst errors. So interleaving techniques to take care of burst errors. Now, the reduction in power which you get by way of doing coding is normally defined by a quantity which is called as coding gain. So coding gain is very important concept, coding gain. So let us denote this as gamma. This will be 10 log to the base p power required when you have uncoded signals, divided by the power required when you have the coded signal. So this indirectly tells about the reduction in power by having coding in the bits, coding in the waveform. So this is called as coding gain. And if I calculate the capacity of FSO link under background noise, this can be given by a formula which is C log 2 exponential lambda s, and this is say P, which is PAPR. I'll explain about this, into 1 plus 1 by psi log natural 1 plus psi minus 1 plus PAPR divided by psi into log natural 1 plus psi divided by PAPR. So this P is peak to average power ratio, PAPR. What is the peak power in the signal and what is the average power in the signal? So this ratio is called as peak to PAPR, peak to average power ratio. And this psi is number of photons, signal photons divided by number of background noise. So this is photons in the signal, and this is the background noise. So this is how the channel capacity of FSO link is defined in terms of PAPR parameters and these lambda s, the number of photons required for the signal for correct detection of the received signal, and lambda b is the background noise. And so if you see here, this C will increase if you have high PAPR. And high PAPR can be obtained by using, for example, MPPM kind of modulation, which we will discuss in later lectures when we discuss about the modulation part. So that is why in FSO system you will see, a use of this particular modulation techniques, because it gives you enhanced capacity. So this is one way. Another way of handling or mitigating atmospheric turbulence. And if I plot, for example, in this case, this is a PAPR, and this side is channel capacity. It will be something like this for different values of psi, and psi is lambda s by b. So this is, for example, 20, this psi is equal to 15, and this psi is equal to 10. So as your PAPR increases, there is a improvement in the channel capacity as given by this formula, and it is plotted here in this graph. And that is the main motivation for using multi-level or multi-pulse position modulation techniques for FSO communication. Another method which can be used for mitigating the atmospheric turbulence is use of both RF and FSO. So normally what is done here, you have the input stream, and then this is a switching block. or switching at the transmitter, switching at the transmitter. So this is switching. And then you have two systems. One is FSO transmitter. The other one is RF transmitter. Because if you see FSO, they are very sensitive to fogs, those kind of disturbances. And whereas RF is more sensitive to rain kind of, this is fog, rain, because the dimension of the rain droplet is somehow similar to the lambda. So under rain conditions, RF may fail. Under fog conditions, FSO may fail. So depending upon the situation, either you switch to FSO or you switch to RF. That is why one requires a combination of free space optics and a backup RF link. So this is FSO link, for example, and this is, the RF link. And this side you will have FSO receiver and you will have RF receiver. And then you have another switch here. This is switch or switching. So there are two options available. One is hard switching, which means either you are getting signal from the RF part or from the FSO part, depending upon the situation. So this is called as hard switching. So either FSO link is working or RF link. The second option is soft switching. So here actually both are used for decoding. So both coordinate, both the systems coordinate. So essentially you get signals from both the arms and then you process it to get more advantage. So this is called as soft switching. So if you do this, having both RF and FSO link, so your availability of the system or the reliability of the system increases, and the link availability is actually can be defined as one minus P outage. This is for the FSO part, multiplied by P outage for the RF part. So this is actually outage. Into 100 if you want to have in percentage. This is in percentage. So the link availability improves if you use two systems, the transmitter and switcher, and then there are two options available, either hard switching or soft switching. Soft switching gives still better performance as compared to hard switching, but it's difficult to implement. Hard switching is easier to implement. So this we will also analyze in future classes to analyze the improvement in the link availability if I'm using both hybrid RF and FSO system. So these are the few methods for controlling or mitigating the atmospheric turbulence. So we will stop the discussion on outdoor modeling now, and next time we will discuss about how to model a underwater system. So that will complete the modeling of all the parts. So we started with indoor modeling. We have now done outdoor modeling, and the third is we are going to do underwater modeling, and then we'll move on to different modulation schemes which are required for different systems, whether it is indoor or outdoor or underwater. Thank you.